Hi guys, let's continue our topic maximum likelihood estimation. Today we will solve more questions how to find maximum likelihood estimators using differentiation method and how to find maximum likelihood estimation by inspection where the range of a random variable depends on unknown parameter. Okay. Let's remember the likelihood function first. We use L notation to represent likelihood function. Likelihood function is a function of unknown parameters or given the sample information. Okay, usually we use L theta notation. So it shows us how likely to obtain the specific theta when we observe this data set. So how likely, how plausible to get specific theta value for a given sample. Mathematically, we found this function, likelihood function, by using the joint PDF. Definitions are totally different, but mathematically they are equivalent. Okay. So if I ask you to what is the meaning of likelihood function, don't tell me it's the joint PDF. Okay, so it's not. PDF is a function of random variables given some specific theta value, but likelihood function is a function of theta and it shows us how likely to obtain that specific theta for a given sample. And so for a given sample, basically, if you want to find some estimator based on sample, we want to maximize this likelihood function. So maximize L theta in the parameter space for a given sample. So which statistic, if I replace theta by some statistic, which statistic maximizes this likelihood function, we want to find that. Okay, so maximum L theta, theta in the parameter space, solve for this and get theta had acted as the maximum likelihood estimator. One tool to do that, so this is the maximization problem basically, and instead of most of the time log likelihood function, we use log likelihood function. So what we are doing basically, taking the derivative of the likelihood function to see where likelihood function maximize or minimize basically, and solve for theta. Get this one, but you have to check the second derivative also because this calculation gives us the minimum point also, or the maximum point, so we have to make sure that at theta hat this function is maximized. If this is the case, this is the MLE of theta. Okay, so let's solve some questions. Most of the time you can use this approach to find the maximum likelihood estimator, but there are some places that we cannot use, and mostly the range of theta is continuous, but sometimes the range of theta discrete. So in that case we have to use a different strategy because if theta is continuous, then we can differentiate the likelihood function with respect to theta, but if it is discrete, then we cannot use differentiation, you know. So by replacing theta value on our likelihood function, and for which value which value of theta our sample point gives maximum likelihood, so we have to check that actually. So we will see some examples in the class. I also show you one example on last Wednesday. Okay, so let's look at an example. So we will see several examples. Okay, so let's say we have a random variable x with the PDF. Here the PDF is given, so it's a negative binomial PDF actually. Okay, so range of x is discrete, but the range of theta is continuous here. Okay, so we can use differentiation. So find the MLE of theta is the question. Okay, so first of all, find likelihood function as a step one. Okay, so multiply So assume that here, let's say we have a random sample of size n. Okay, so let's assume that. Okay, let's write likelihood function. So it is a multiplication of marginal PDFs, for a random sample. Okay, so multiply our PDF xi plus 1 theta square 1 minus theta to the xi I from 1 to n, and obtain the likelihood function as 2 to the n 1 minus theta to the summation xi, where theta is between 0 and 1, so it's the function of theta. So you have to give the range for theta. Okay, so to make calculations easier, actually you can take the derivative of theta using likelihood function, but you have to use differentiation for multiplication. It's kind of much more, how to say, long to get the result. So to make the calculations easier, find the log likelihood function. Ln of multiplication gives us summation of ln's, plus 2n ln theta plus summation xi ln 1 minus theta. Okay, so we obtain the log likelihood function, and then take the derivative with respect to theta now. Okay, so in the first part we don't have any theta term, so this term will be 2n over theta. So we have minus summation xi over 1 minus theta equate this to 0, and so for theta. We obtain theta as 2 over 2x bar after some calculation. Okay, so let's put a cap here. So because it's not the exact value of parameter, we don't know that. This is just the estimator. But we have to be sure that our second derivative is negative. So our likelihood function is concave down shape. So it has a maximum point. Okay, so theta equal theta hat. So this should be negative. So when you check that, you will see this is correct. Okay, so after that we can check the properties of this estimator basically. So this is our now estimator. Then we can check some properties, good properties, to be a good estimator. But we will see that later. First of all, let's find the estimators, then discuss their properties. Okay, so let's look at another example. This looks like the example that I solved on Wednesday, but it's a bit different actually. So let's check. So suppose that x is a discrete random variable, but here theta is continuous. Suppose x is a discrete random variable like binomial or Poisson, but the PMF is given in the following PMF with the parameter space for theta such that theta is between 0 and 1. So this information given to us, and also this information given to us, the PMF of x. X can take only 0, 1, 2, and 3. The probabilities of getting 0 is 2 over 3. 1 is theta over 3. Getting 2 is 1 minus 2 times 1 minus theta over 3. And observing 3 probability is 1 over theta over 3. So this PMF is given to us. And this information, also another information given, the following 10 independent observations. Now we have the sample points. Observations were taken These are 3, 0, 2, 1, 3, 2, 1, 0, 2, and 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So what is the MLE of theta is our question. What is the MLE of theta? Okay. So let's so we have all the information. We know the sample size, it's 10. So let's find the likelihood function, and we know all the given values of the sample points. So let's write likelihood function. So this should be our first step. Okay, so what is the first observed value? Probability that x equals 3. So this is the multiplication of marginal probabilities, and also probability that x equals 0, probability that x equals 2, probability that x equals 1. So it goes on like that. The last one, x equals 1. So let's so how many trees we have? 1, 2 only. So let's write the probability of observing 3 as 1 minus theta over 3. We have 2 theta values. Take the square. Let's look at 2. Okay, so how many 2's we have? 1, 2, and 3 2's. The probability of observing 2 is this one. Get the triple. And then let's look at 1. Probability of observing 1 is 1 theta over 3. How many 1's we have? 1, 2, and 3. And 0 we have the probability of observing 0 is 2 theta over 3. How many zeros we have? Only 2. Okay, so this is the likelihood function. Okay, let's find the log likelihood function to make our calculations easier. So here the range theta is a continuous parameter. The range of the theta is in a continuous plane. So let's find log likelihood function. Okay, so we have 2 times ln 1 minus theta minus ln 3. Okay, and okay, so we have plus 3 ln 2 times 1 minus theta minus ln 3, and plus 3 ln theta minus ln 3. Okay, and then 2 ln 2 theta minus ln 3 again. Okay, so when we look at the form actually, so we will see that so we have several 1 minus theta values, and also we have several theta values. Okay, so let's write this one as ln 2 plus ln theta, and let's write this part is ln 2 plus ln 1 minus theta. So we will have exact ln thetas and ln 1 minus thetas. So let's forget about the constants, because when we differentiate log likelihood function with respect to theta, constant terms will disappear. So our log likelihood function is proportional to how many ln thetas? So we have 2 from here, we have 3 from here, just that. Yeah, 5 ln 1 minus theta we have. Let's count the ln theta parts. So we have 3 ln theta here and 2 ln theta here. Again, 5 ln theta parts. Okay, so let's try to solve that, and we try to find the maximum point, d ln l theta over d theta. Okay, so we have minus 5 over 1 minus theta plus 5 over theta. So we have minus 5 theta plus 5 minus 5 theta over theta 1 minus theta, equate this to 0. So we will have tan theta equals to 5. So theta should be 1 over 2. Put a cap. Okay. So we have to check the second derivative also. When we do the second derivative, let's see. So we have positive values. So it is negative, I think. Okay. Okay, so it is this one. So theta hat is in the range of the parameter space 0, 1. So let's check MME of theta here. Okay, so what is the MME of theta? Find the expected x. Okay, so 0 times 2 theta over 3, 1 times theta over 3 plus 2 times 2, 1 minus theta over 3, and we have 3, 1 minus theta over 3. So expected x is something. I didn't calculate it. But when you calculate it, you will get what? So we will have theta plus 4 minus 4 theta plus 3 minus 3 theta over 3. Okay, so when we equate expected x to x bar to be able to find the MME of theta, we observe that our MME calculated as 5 over 12. So they are different than each other. So now we have to discuss which one is better estimator, theta hat or theta tilde. So we will discuss their properties later. Okay, so let's focus on example with 2 unknown parameters. Very simple one actually, we use it a lot. Normal example. How to define the MLEs of mu and sigma square. Okay, mu sigma square, and here let's assume that again we have a random sample of size n. Okay, and the parameter space for mu and sigma square, we know we have mu and sigma square such that mu is in the real line and sigma square is a positive quantity, sigma square. Okay, so this is parameter space that we have. So let's write the likelihood function. I hope you know the PDF form of the normal distribution. You have to know as a statistician. So we have a random sample. So it is the multiplication of the marginal normal PDFs, I from 1 to n. And so what is that actually? So we have 1 over 2 pi sigma e to the minus xi minus mu whole square divided by 2 sigma square I from 1 to n. Or we can write this as 1 over 2 pi sigma square n over 2 e to the minus summation xi minus mu whole square divided by 2 sigma square. And we know that the range of mu and sigma square. Since likelihood function is a function of parameters, you have to give the range of the parameters where this function defined for unknown parameters. Okay, so we have 2 unknown parameters. So we have to differentiate our likelihood function twice. So we have to get the partial derivatives now. First of all, before that, actually, let's find log likelihood function. Okay, so we have minus n over 2 and 2 pi minus n over 2. So keep sigma square as sigma square because our variance is sigma square. We want to find the limit of sigma square. So it's like think sigma square as a, for example, okay, not a square term. So sigma square minus summation xi minus mu whole square divided by 2 sigma square. Okay, so now get the log likelihood functions for mu. Okay, so in the second part we have only mu term. Okay, so this part. Get the derivative of that. So we have minus sign coming from here. So we have 2 summation xi minus mu 2 sigma square equated to 0. So here we can definitely directly get the closed form solution for the mu. We don't need the second equation and we don't need to solve system of equations. So do the same thing for sigma square. Okay, so we have minus and 2 sigma square plus summation xi minus mu whole square 2 sigma to the 4. Okay, and then equate this to 0 and obtain sigma squared as summation xi minus mu whole square divided by n. Okay, so put the caps here. Then the MLE of sigma square will be summation xi minus x bar whole square divided by n. So MLE gives us a biased solution. The denominator is n, not n minus 1. Be careful about that. So basically we have to also check the second derivatives here, like, but you don't have to do that. Mu square the second partial derivative with respect to sigma square, and actually we have to say sigma to the 4 minus the ln the mu, the sigma square, this should be positive, and when we consider this, mu square should be positive at mu hat and sigma hat square. Okay. So let's give let me move to another video, because if it's too long then I cannot download to YouTube. So I will stop here and continue with another example.